Well, hello and welcome. In this video, I'll be covering section 5.4, which is over the properties of logarithmic functions. My goal for you by the end of the video is to be able to convert from logarithms of products, powers, and quotients to expressions that are in terms of individual logarithms, as well as the exact reverse of that, and simplify expressions of the type log base b of b to a power of x, as well as b to a power of log base b of x. So the first logarithmic property we're going to talk about is the property of a product inside of a logarithm. So essentially this is very similar to one of the product rules for exponents, where if I multiply two things with the same base, I add the exponents. Key part of that being the fact that I'm adding up in that exponent area. The product rule for logarithms is if I have a product inside, I can turn it into two logarithms with the same base. So notice in this case the base of b stays the base of b, but the product that's inside I split up into two logarithms separated by addition. So again, kind of the key takeaway here is if you remember the exponent rule where you multiplied two things with the same base, you would end up adding them together. It's very similar in this case that when you have multiplication inside, you're going to add them together as two separate logarithms. So basically, the logarithm of a product happens to always equal the sum of the logarithms of each of the factors. So to kind of show how this is going to work, I'm going to go ahead and just separate this product. Notice I have 9 times 27 inside. So since that's a product, I can turn this into a sum of two logarithms. The base was 3, so I make sure that I keep it 3. Then it would be of 9, and then added with log base 3 of now 27. Now each of these, technically I would be able to reduce, because after all, 3 to what power equals 9? Well, 3 to what power equals 9? That would just be a power of 2. And then 3 to what power equals the 27? Well, 3 to the third would be 27, so this would be a plus 3. So technically this could have actually been simplified and just turned into a value of 5. But really all this question was wanting us to do is just express it as a sum of logarithms. So technically right here, I had satisfied whatever the problem was. This just happened to be one that we were able to simplify, so I figured why not, let's go ahead and do it. And if we can take a single logarithm, like that last example that had multiplication inside, and separate it into two logarithms, we can actually go the other direction and take multiple logarithms that are separated by addition, as you can see here, and go ahead and multiply it over, or multiply it inside. So this one, I have a log base 2 of, and then it would be the two parts that are inside, so in this case the p to the third and the q, that would now be multiplying inside. And that's essentially it. So notice again, anytime I have this addition in the middle, I just turn it into a product inside of a single. So notice I had two logarithms to start, now I only have one logarithm. So more times than not, this really is the process we'll go through and do, because if we can have fewer logarithms, probably the easier it's going to be. So the next property or rule I'm going to go ahead and talk about is what's called the power rule. Now it's similar to, kind of comes from, I guess is another way of saying that, the idea of when I did a power to a power, I multiplied the exponents. Kind of similar thing is going to happen here with the power rule, in that if I see a power, what ends up happening is, in this case, notice we have the power of p that's right there. What we can do is just move it in front of the logarithm and turn it into a coefficient. The reason this would happen, if we maybe just did a relatively basic example, if I said, okay, let's think back to the property we just talked about. If I had the log base 2 of, and let's say I had x squared on the inside, that really would be the same as saying log base 2 of an x times an x. And so according to the product rule or product property, I should be able to, because that's a product inside, separate that into multiple logarithms, both with the same base, and add them together. Well, in this case, these actually would be like terms, hence the repeated multiplication that's inside, which is really what a power is doing. Notice what that would do is turn into something we can actually just write as a single logarithm, but now have a coefficient in front, because if I have a log base 2 of x adding with another log base 2 of x, I really could simplify that and just say, hey, I have 2 of those log base 2 of x's. And then kind of the connection to make here is, notice the original power of 2 just became the coefficient on a single log, and then what was inside still remained the x. So that's another way that you can kind of think of, why does this rule work? Ultimately, it's a power is repeated multiplication. Instead of having to write it out as that repeated multiplication like I did right here, and then separate it into a series of logarithms that are added together, all of those logarithms, if I did do that, would be identical, such that I could then combine like terms and turn into just a coefficient in front of that by adding the coefficients technically that were in front, which in this case were a 1 and a 1, to come up with the 2. So to practice this one, let's go ahead and just try a few out. Notice each of these have an exponent. This one in the middle, I'm going to do a quick little review. Remember, anytime you had some base being raised to anytime I had like a radical with maybe some index here and maybe even some potential power on it inside, remember the way that we can convert a radical into an exponent is I still keep whatever the base is, whatever the power inside goes in the numerator, and whatever the index of the root would go in the denominator. So in other words, if I said what would be a different way I could rewrite the square root of b, well, b would be raised to a power of 1 on the inside, and if I don't see a number, remember the index would be a 2, so this would just turn into b to the 1/2, and so on and so forth. So that will hopefully help with the how do I rewrite this middle one when we get there. But anyway, the first one, notice I have this -3 that's up in the exponent area, so power rule says I should be able to just move that in front. Or not power rule. Yeah, it is power rule. Sorry. I second-guessed myself there for a second. But essentially that power just comes out as a coefficient, and now I have a logarithm that has a little bit smaller or easier number to deal with that's on the inside. This one we don't know what the base is, so I wouldn't really be able to evaluate this, but the concept of being able to move the power out front really is all we're trying to practice. The next one, if I were to try and rewrite it using an exponent, this would be log base a of, and then on the inside I could say this really is a 7 to the first power inside, but then I have a 4th root, so that would really be like a 1/4 power. Again, the 1 on top is because there's a power of 1 on the 7, and the 4 in the denominator because that was the index of the radical. So since that number is an exponent, or that 1/4 is an exponent, I should be able to just move that out front as a coefficient and rewrite this as 1/4 times the log base a of 7. And the very last one, just to demonstrate that yes, we do have other logarithms that have bases. In this case it's the natural log, so it's a base of e. Not that that really matters a whole lot for this rule. I'm just going to take whatever power I see, move it in front, so this would be able to be rewritten as 6 times the natural log of x. So hopefully this rule is not overly complex. It's just if you see a power, it has to be on everything that's inside of the logarithm. Notice all of these just had a single thing on the inside. But if I had something like log base 2 of like x squared plus 1, something like that, this power I wouldn't be able to do anything with, like that part, because there's addition on the inside. I wouldn't be able to move this power out front, whereas if it would have been log base 2 of x plus 1 squared like this, then that one I would be able to actually move the power out front, and it would still remain addition on the inside. So just kind of want to point it out that you have to have the power on everything that's on the inside, not just an individual part. So if you have something like this first example right here, we can't really do anything as far as the power rule is concerned. However, if the power is on everything like it was with the second example, then I actually can do the conversion, or at least move that power out front. So just wanted to do another random example, as well as a potential place where maybe a mistake might be made. Just realize that powers have to be on all of the inside. That's kind of the moral of the story. And the next property, or really the last property with logarithms here that we'll have to worry about, is what's called the quotient rule or quotient property. And again, this is involving logarithms. So if I have a quotient inside of a logarithm, so notice in this case it has m being divided by n, the order in which that division happens is important in this case. Whatever's in the numerator will always go first, and then I subtract whatever was in the denominator, and notice I split it up into two logarithms when it's all said and done. And this kind of relates back to the quotient rule for exponents, where if I divided two things with the same base, I subtracted the exponents. Notice subtraction and subtraction are going hand in hand. So essentially what we have with this one is if I have a logarithm of a quotient, then that turns into a difference of two logarithms, where it would be the numerator first and then minus the denominator second, but now as two separate logarithms that still keep the same base. So to help make that make sense, let's go ahead and just see an example of how do I rewrite a single logarithm as a difference of multiple logarithms. Well, inside, notice we do have a quotient, so I can rewrite this as log base t of the numerator, so 8, then minus log base t of the denominator, which in this case was w. And that's it. So notice all we're doing is just trying to find a way to either take a single log and separate it, or potentially taking multiple logs and combine them together. So if I saw two logarithms with subtraction between, I know I would be able to divide inside of a single logarithm. So speaking of that example, notice this one has two logarithms that are separated by subtraction. So I should be able to actually combine this and turn it into a single logarithm. So it's going to be a single logarithm with a base of b of, and then it's always whatever is first goes in the numerator, so in this case 64, but then divided by whatever was second or after the minus sign, which is the 16. Now this one, 64 divided by 16 can actually be simplified even further. So I'm going to go ahead and just rewrite that as technically it would turn into a log base b of 4. Now some common errors or mistakes that students make when first learning this is thinking that if it's multiplying inside, you're just going to multiply outside as well. Remember, multiplication does need to turn into addition between the logarithms. Just like if I had addition inside, I can't separate that out. In other words, logarithms don't distribute through the parentheses. It's not a multiplication idea. The parentheses in this case are telling you what's inside of the logarithm. So it does not follow distributive property. The other common misconceptions is I can't just have a power that's on the entire log and move the power out front. The power has to only be on the inside portion. So notice the very subtle difference here is there was the extra parenthesis, and that power is outside. So the power is technically actually on the log as well, which that means I cannot move it out front. It's not how that property works. And then the other common mistake is if I have two things divided inside, thinking that I'll just keep it as division. Remember, division when I separate will turn into subtraction. So the next few are just going to be some examples that kind of throw even more at you, and it wants us to do basically as much as possible. So the first couple here are going ahead and separating a single log into as many logs as possible. So let's go ahead and just look at what we have. This would be able to turn into, looks like I have a product in the numerator, but then I have a quotient at the end. So I'm going to go ahead and just do the product part first. So this would be log base b of x squared. Then because it's multiplying, I'm going to go ahead and use addition. Be log base b of the next part, so y to the 5th. But then I'm dividing by z to the 4th, so that's going to turn into subtraction. And I've got log base b of z to the 4th. At this point, notice I ended up getting some powers just on the inside portion, so I should be able to actually deal with those as well. So those powers, because they're in that spot, should be able to move out front and become coefficients. So my final result for this one would be to rewrite this as 2 log base b of x plus 5 log base b of y, and then minus 4 log base b of z. And when there's only a single thing, you don't have to put parentheses, but if you prefer throwing parentheses around things, we could have put parentheses here, here, and here, which then would have meant in the next line it's just around only the letter. But again, with logarithms, it's implied if there's only a single thing after it, that only that thing is inside of that specific logarithm. So any operations afterwards, in order for that operation to be inside of the logarithm, they would have to have the parenthesis extend further beyond it. So with these, even if I didn't have the parentheses, it would be implied that only x was in the first log and only y was in the second log and then only z was in the third one. But if you prefer the parentheses, have at it. That's just as good. I'll go ahead and try another example here. So this one, we've got a radical. So first thing I would want to do is go ahead and rewrite that inside part using an exponent. So this would be a squared b over c to the fifth. But a cube root really is like a 1/3 power. So I'm kind of at a juncture where I've got a couple of options. I could just distribute that power to each of the parts and make that a to the 2/3, b to the 1/3, and c to the 5/3, or I could use the log, one of the log properties, and just say, you know what, let's just take that power and move it out front. I'm going to go ahead and do that strategy. So the 1/3 is going to come out front, and I can rewrite this now as a 1/3 times the log base b of just what's inside. So a squared b over c to the fifth. Now when I separate this logarithm, because there is a product and a quotient inside, I should be able to, if there's 3 parts, turn into 3 different logarithms. I'll have to remember that this 1/3 is actually going to be multiplying all of it. So I'll go ahead and open up a parenthesis for, let's make sure that we distribute that through here in the next step. But the first one, a squared times b, is going to turn into addition between those 2 logarithms because it was a product. And then it's going to be subtraction for this c because I'm dividing by c, so it would be log base b of c to the fifth. And just like earlier, I did have a couple of powers that resulted, so I can move those out front. This middle one is actually kind of nice because log base b of b itself actually equals 1, so I should be able to simplify that and maybe move it to the end, or I guess I can just keep it exactly where it is. So this would now have still the 1/3 in front. I'll need to distribute through here in the next step. The 2 is now in front of this logarithm, again because of the power rule. I'm going to go ahead and replace log base b of b has a value of 1, and then minus the 5 log base b of c. So now that I can distribute this 1/3 through, let's go ahead and take it in, and my final result for this one is going to be 2/3 log base b of a, then plus a 1/3, and then minus a 5/3 log base b of c. And there's my final result for separating this one into a sum or difference of logarithms. Tried another example. It's a little bit more complex. This time notice I'm actually dividing by more than one thing, and there's a product in the denominator, so this one I'm actually going to need to kind of group things together. So without further ado, let's go ahead and start this. I have a product with a and y to the fifth, so I should be able to turn that into 2 logarithms with addition between them. Then I have division, but it's a product on the bottom, so I'm going to have to group these ones up and distribute that minus through eventually. So this would be a log base b of m cubed, and again it's a product, so it's going to be plus log base b of n to the fourth. The other way you can think of it is anything that comes from the denominator will always just have a minus sign in front of it, because as you can see, hopefully with the next step, I would need to distribute this minus through, so both of those terms will turn into, or both of those logarithms will turn into negatives. I do also have, notice, a couple of powers that should be able to move out front, so I'm going to go ahead and just say, okay, the 3 is going to come out front, and the 4 is going to come out front, and the 5 that was on the y. So this now can turn into log base b of a plus 5 log base b of y. Then I've got minus 3 log base b of m, and then minus a 4 log base b of n. And again, the reason that that one got the minus sign is just distributing the subtraction that was in front of the parenthesis through, and now that gives me my most separated in terms of addition and subtraction, as well as having coefficients version. Notice I took 4 things that were inside and it turned into 4 logs. So you can always kind of look at how many things are multiplying or dividing inside and kind of expect or think ahead and expect how many logarithms you actually will be able to have as your final result. So if we were able to take a single logarithm and separate it into multiple logarithms, hopefully it would be reasonable that we can start with multiple logarithms and turn it back into a single logarithm. So that's what all of these examples are going to be. And then you always look to see if maybe potentially you can simplify some of the parts once you have everything inside. So we kind of go the exact reverse order of what we were doing with the last example. Notice the last thing normally we did was deal with the exponents. Now that actually is going to be the first thing that we deal with. So if we ever have coefficients in front of logarithms, the first thing we would need to do is take those up and make them powers. So notice with this first example, there were 2 different coefficients, so I'm going to move them up and make them powers right off the bat. So this can now be rewritten as log base b of x to the 5th minus the log base b of y, and then plus the log base b of z to the 1/4, and I'm going to go ahead and rewrite the 1/4 back in radical form. Don't necessarily have to, but I kind of prefer writing the radical as opposed to having a fraction as a power. So with this, now let's go ahead and think in terms of, well, what really do I have? I have the ability to take each of these things, and since they're separated by addition and subtraction, I should be able to find a way to combine it and make it one single logarithm. So the way I do that is basically just say, okay, well, it's going to be a log base b because that's what it's been the whole time. And then I would have x to the 5th being then divided by a y, but then that result would be multiplied by the 4th root of z. Well, anytime you multiply with fractions, essentially it would just go to the numerator if it didn't have a specific denominator at all. So you could picture that like it was maybe over a 1, so that the x to the 5th and the radical would multiply, and then on the bottom it would have just been a 1 times y, so it would stay a y. So notice I was able to now accomplish making it a single logarithm, which again was the whole goal of this particular problem. If there was anything I could reduce, I would go ahead and do it, but z, x, and y don't really share anything, so there's really no reducing that could have happened. If we move on to the next one, notice I have 2 logarithms. They happen to be natural logs this time, separated by subtraction. So since there's subtraction in between, I should be able to combine it and utilize division. And in this case, with a quadratic getting involved, it's possible I might be able to factor that. So I'm going to, at the top, just kind of go, how could I factor that? If I had 3x squared minus 5x minus 2, my approach would be, let's multiply the a and c values. So 3 times negative 2 is negative 6. What multiplies to negative 6 that would add to a negative 5? Well, that should be a negative 6 and a positive 1. However, I have this 3 as the coefficient, so remember I'm supposed to divide by 3. The first one does reduce to an x minus 2, but the second one doesn't reduce, so I bounce the 3 in front, and that turns into 3x plus 1. So if we look at what we have, this really has turned into, if I replace the denominator, I've got 3x plus 1 over an x minus 2 that's multiplying with a 3x plus 1. And so as we can hopefully see here, I have a 3x plus 1 that's a common factor on top and bottom. So those should be able to reduce. And that leaves my final result here of this really would be like the natural log of, and then all that's left on top would be a 1 over the x minus 2. And there's my final result for this one. So now that we kind of generically hopefully understand how we can either separate logarithms or combine logarithms, I'll go ahead and display a type of problem that could be presented. So notice this gives us some values of specific numbers. So log base b of 2 apparently comes out as about 0.301. Since I don't know what the base is, I really don't know, like I wouldn't really be able to type this into a calculator, in other words. The other one it says is log base b of 3 happens to have a value of 0.477. So what our goal is essentially to take advantage of knowing those two numbers. I can raise them to powers, I can do all sorts of different types of things, just try and rewrite them, or at least the numbers that I've been given, I want to try and rewrite using either a 2 or a 3, and technically there's also one that we weren't given that should be known, which is the log base b of 1. Anytime you plug 1 into it, you should always get 0 back. So this one, even though it wasn't provided for us, we can always use that property of logarithms. Anytime 1 is inside, it would just have a value of 0. So let's look at this first one. If we think of, okay, I wasn't given 6, but with the numbers I was given, a 2 and a 3, there is a way that I could make that 6. I really could rewrite this as log base b of 2 times 3, which then means I could separate it and call it log base b of 2 plus a log base b of 3, and now actually replace with the values that they gave us. So in this case, log base b of 2, it said was 0.301, and log base b of 3 was 0.477. So if I add those together, I should be able to get that this would equal 0.778. Now if we look at the second one here, part B, it already had 2's and 3's, or some version of a 2 and a 3 on the inside. So what I could jump straight to is, because that's division, I can separate that into 2 logarithms that are being subtracted. And so in this case now I have what those values are. They again were given to me, so I could replace the log base b of 2 with the 0.301, and then it's going to be minus the value of log base b of 3, which was the 0.477. And if I were to now subtract those, 0.301 minus 0.477, I get a value of, for this one, a negative 0.176. Moving on to the part C here, rewriting 81. I feel like there's a way I can rewrite 81 using an exponent. So in this case, I could rewrite this as, this is the same as log base b of, and then 3 really raised to the 4th power is 81. So I could rewrite this as 3 to the 4th, which then allows me to, by property rule, move that 4 in front and call this 4 times log base b of 3. And now go ahead and replace what log base b of 3 is. So this really is going to turn into 4 times the 0.477, which would come back as a result, go ahead and write it underneath, I guess, of 1.908. The next one here has division on the inside, so once again I can go ahead and separate log base b of 1 minus log base b of 4. Well, log base b of 1 is just going to equal 0, so this really is equal to a negative log base b of 4, but I could also rewrite that as 2 squared. Since I was given the number 2, I want to try and find a way to use either a 2 or a 3. 3 doesn't seem all that helpful, but 2 does. Since 4 is equal to 2 squared, I could now just say, well, let's just move that 2 out front, so this would turn into a negative 2 times log base b of 2. And now I can replace with its value, which log base 2 of 2 was the 0.301. And if I double that, that would turn into a negative 0.602. These last two examples are potential kind of tricks. This is where the find each of the following if possible happens. This next one, if I said, okay, you have a value of 2 and a value of 3, let's find a way to make a 5. There's really no way by multiplication or division or using exponents, any of the rules that we have, to really replace 5. So with part E here, we basically can't find or cannot evaluate from the given info. could we make that 2 plus 3 on the inside? Absolutely, but having addition on the inside is not something I can really separate. It's only multiplication or division, or potentially the use of an exponent. So since 5 was something I can't really get from a 2 and a 3 by using any of those 3 operations, either multiplication, division, or power, that's why I really would not be able to evaluate it for this particular part. Now the last one's kind of tricky. In this case, it's just 2 logarithms being divided. So ultimately we would just go straight to substituting in. I can't separate division between 2 logs. That just is whatever that operation is. So in this case it would be the 0.477 divided by the 0.301. And if I go ahead and simplify that, 0.477 divided by 0.301, I get a value of approximately 1.58472 according to my calculator. So notice, even though yes, I saw division, it wasn't inside of a logarithm, so I actually was just able to replace and do the division. Now the last couple of concepts we have are the how do I simplify some expressions that look relatively intimidating. And if we think about why we would care about doing something like this, well, ultimately it would be involved if I were to try and solve something, and that's kind of where we're headed. That's going to be what our next section is solving these expressions that have either logarithms or exponentials. And because they're inverses of one another, if I start with an exponential, more than likely I'm going to need to utilize a logarithm, and vice versa. If I have a logarithm, more than likely I'm going to need to utilize an exponential. So the 2 different types that we could have a exponential inside of a logarithm, and since they are inverses of one another, as I just mentioned, it really should cancel each other out and just leave whatever is in, for this scenario, in the exponent area. So notice in this case, if I have log base b of some b being raised to a power, the result is just going to be the power. So to put that property into action, let's go ahead and just see how kind of simple that really can make things. This first one, if I look at it, I've got log base a, but then inside it has a to the 8th. That's really just going to turn into 8. Or if I look at part B, the natural log has a base of e, so since that base matches the base of the exponential on the inside, it's just going to cancel out, leaving just the exponent. So in this case, negative t. And I don't know why I wasn't boxing them up as I go. There we go. And then the last one, a common log. If I don't see a number, remember there's like a base of 10 right here. Since that base matches the base of the exponential, they are inverses of each other, so it will just leave what's in the exponent, which in this case is 3k. Now a different way that we could have also approached this one, I'll just use part A as an alternative way of doing it. Keep in mind, if I have an exponent like that, I could move that out front. And then something we talked about earlier is anytime the number inside matches the base of the logarithm, it would be really like a to what power is a. Well, that would just equal 1. So I could have actually approached it that way and eventually still got to where it was 8. So notice both directions worked out, but definitely if we recognize, hey, I have an exponential inside of a logarithm and they're inverses, or they match as far as their base is concerned, take advantage of, well, they're just going to have an inverse relationship, so it's just going to leave the power. That would kind of have saved me from having to use any of those rules and do like the 3 steps that I did here. Notice we were able to actually answer those in just a single step, so long as we knew that that was how the relationship worked. So hopefully it makes sense. If it worked out such that an exponential inside of a log, when the bases match, would cancel each other out, hopefully it seems reasonable that now we can have also a log that's inside of an exponential, and as long as their bases match, they would also cancel. So again, it's that idea of they're inverses of each other. So in this case, if I have b being raised to a log or a power of log base b, those are inverses of each other, so it just should leave what is inside the logarithm. So notice in this case it does just turn into an x. So basically, if I ever have b being raised to a power of a log that matches the base, then it's just going to be whatever is inside the log that would be left over. So as we can see with this first example, I've got 4 being raised to a power of log base 4. The 4's match, so that should cancel, leaving me just what's inside, which was k. Or the next one, e and natural log, they have the same base. The natural log is up in the exponent area, so those should cancel each other out, leaving me just the 5. Or the very last one here, 10 to a common log. Again, there's an imaginary 10 right there, or a 10 that we could add into it. So since those two bases match, it should cancel, and it would leave just what's inside. So hopefully you can kind of see how nice and easy those steps can be. It's just a matter of getting used to it, because anytime something's new, it's always a little bit confusing. But the more you practice it, hopefully the easier that becomes to recognize. Anywho, that will be it for this, but hopefully you feel like at this point you understand how the rules for properties or for products or quotients or powers work with logarithms, and how you can separate into multiple logarithms or take multiple logarithms and combine them together to turn into a single logarithm, as well as some of the ways that we can simplify. But as always, if you have questions, just reach out and let us know, and we'll do our best to try and make it make sense. As always, I also appreciate you taking the time watching the video. We'll catch you guys next time.